CPU architecture, ALU, CU, registers. Here is your same structured, beginner-friendly content for CPU architecture, ALU, CU, registers. Intermediate level introduction. The CPU, central processing unit, is often called the brain of the computer, but internally, it is made up of smaller components that work together to process instructions. At the intermediate level, understanding CPU architecture means learning about its core internal units. ALU, arithmetic logic unit, means performs calculations. CU, control unit, means controls and directs operations. Registers means store fast, temporary data. These components work together to execute every program you run. Understanding CPU architecture helps learners understand how instructions are executed, connect software operations to hardware actions, improve debugging and performance knowledge, prepare for advanced computer architecture. What is CPU architecture? CPU architecture refers to the internal design and organization of the CPU. It defines how instructions are processed, how data flows inside the CPU, how components interact. In simple terms, CPU architecture equals how the CPU is built and how it works internally. Example concept. Instruction means CPU, means processed, means result, core components of CPU. The CPU has three main internal components: control unit, CU, arithmetic logic unit, ALU, registers. Example concept. CU means controls, ALU means computes, registers means store data. Control unit, CU. What is the control unit? The control unit, CU, is responsible for managing and coordinating all operations inside the CPU. It acts like a manager or supervisor. Functions of the control unit. The CU performs several key tasks: fetches instructions from memory, decodes instructions, controls data flow between CPU components, sends signals to ALU, registers, and memory, manages execution order. Example concept. Instruction means CU means direct CPU actions, how CU works. The CU does not perform calculations itself. Instead, it receives an instruction, interprets it, tells other components what to do. Example. Instruction. Add two numbers. CU sends command to ALU. ALU performs addition. Arithmetic logic unit. ALU. What is the ALU? The arithmetic logic unit, ALU, performs all mathematical and logical operations. It is the calculator of the CPU. Functions of ALU. The ALU handles arithmetic operations, addition, subtraction, multiplication, division, logical operations, and or not, comparisons, x equals. Example concept. Input data means ALU means processed result, how ALU works. The ALU receives data from registers, instructions from the control unit. Then it processes the data and sends results back to registers. Registers, ultra-fast storage. What are registers? Registers are small, ultra-fast memory units inside the CPU. They store current instructions, intermediate results, memory addresses. Why registers are important? Registers are the fastest memory in the system. Example concept. Registers means fastest access means immediate CPU use. Without registers, the CPU would constantly wait for RAM. Types of registers: program counter, PC, stores address of next instruction. Instruction register, IR, stores current instruction. Accumulator, stores intermediate results. General purpose registers, used for temporary data storage. Example concept. PC means next instruction. IR means current instruction. Registers means working data. How ALU, CU, and registers work together. All three components work together during instruction execution. Instruction means CU means registers, means ALU, means registers, means output instruction, means CU, means registers, means ALU, means registers, means output. Step-by-step process. Instruction is fetched from memory. Control unit decodes instruction. Required data is loaded into registers. ALU performs operation. Results stored back in registers. Results sent to memory or output. Role in fetch-decode-execute cycle. CPU architecture is directly tied to this cycle. Fetch means decode means execute. Fetch means decode means execute. Fetch, CU, fetches instruction from memory. Decode, CU, interprets instruction. Execute, ALU performs operation. Registers store results. Data flow inside the CPU. Data flows between CPU components continuously. Example concept. Memory means registers, means ALU, means registers, means memory. This internal flow ensures fast processing. Why this architecture matters. Understanding ALU, CU, and registers helps explain how programs run at hardware level, why CPUs are fast, how instructions are processed, how optimization works. Example concept. Efficient coordination means faster CPU performance. Real-world example. Consider adding two numbers. 5 plus 3. Steps. CU fetches instruction ADD. Data 5-3 loaded into registers. CU signals ALU. ALU performs addition. Result 8 stored in register. Output sent to memory. Advantages of this architecture. Advantages include fast instruction execution, efficient coordination, parallel processing capability, optimized data handling. Example concept. CU plus ALU plus registers means efficient processing, limitations and challenges. Despite efficiency, challenges include limited register size, dependency on memory speed, complexity in modern CPUs, power and heat constraints. Example concept. High speed means heat and power challenges. Concepts learned from CPU architecture. Check. How CPU processes instructions internally. Role of ALU, CU, and registers. How data flows inside CPU. How fetch, decode, execute works. How hardware executes software instructions. This knowledge is essential for computer architecture, low-level programming, performance optimization, system design, simple definition. CPU architecture, ALU, CU, registers. The internal structure of the CPU where the control unit directs operations, the ALU performs calculations, and registers store fast temporary data. Final summary. CPU architecture is built around three key components: the control unit, the arithmetic logic unit, and registers. The control unit manages instruction flow. The ALU performs computations, and registers store immediate data needed for processing. Together, they form a highly efficient system that executes instructions using the fetch, decode, execute cycle. Understanding this architecture provides a strong foundation for learning computer architecture, system performance, and low-level computing concepts.